So my time spent here in going over these topics is going to be limited. I'm going to try to boil things down to the pure essence of what it is you need to know for the exam. When it comes to simple harmonic motion, what we said is that simple harmonic motion involves repetitive motion where the period is the same at any point in time. And the period is the period of time it takes for the oscillator to complete one complete cycle. So simple harmonic oscillation could refer to the wings of a bee moving at a regular rate. It could refer to something even like a pebble stuck in a tire moving around in a circle. That's technically an example of simple harmonic oscillation. But the two that we looked at, and I will talk about them in more detail in a bit, are masses oscillating on springs. And we did lots of lab work and demo work with that where you would hang a spring vertically, you'd put a mass on it, you'd get it oscillating. Okay. And what happens is, we discovered if it takes 2 seconds for the mass to go from the lowest point to the highest point and back to the lowest point, if we walk away from that for a few minutes and come back, we would discover that it doesn't move as far, but it still takes 2 seconds to go from the lowest to the highest back to the lowest point. That's what makes something a simple harmonic oscillator, is the period stays the same. We also talked about a pendulum, and within a certain range of angles, I said less than 10 degrees. I think your textbook says less than 20 degrees. But within a certain range of angles, when you pull a pendulum back and release it, the period, which is the time it takes to go back and forth once, stays the same, even though the amplitude, which is how far it moves, gets smaller and smaller. But in terms of numbers, you need to know what frequency is. It's the number of oscillations per second, and it's measured in hertz. You need to know what period is, and period is the number of seconds per oscillation. And it's measured in seconds. And if you look at how I've defined frequency and period, it becomes quite clear that these things are reciprocals of each other. Oscillations per second is mathematically the reciprocal of seconds per oscillation, and that's why we have this formula that ties the frequency and the period of a simple harmonic oscillator together. Period equals the reciprocal of frequency, right? And that's nothing new. We learned about that when we talked about circular motion, but here we're talking about either a frequency and a period of an oscillator or a frequency and a period of a wave. Because don't forget, a wave, jumping ahead a little bit, a wave is simply a whole bunch of simple harmonic oscillators dancing to the same beat, but slightly out of tune with each other, slightly out of step with each other, right? And again, I'll just show this to you. I showed it to you yesterday, I believe. I don't know what the context was. But when we take a look at this situation here, or move that point, if I were to add a point over here, what's happening on this wave is a simple harmonic oscillation of that point. And that arrow, by the way, is showing the velocity, and I'm not really interested in that. But that point is oscillating, and I can increase the frequency so you can see it maybe more as an oscillator and less as a wave. But if I add another point close to that, you can see that they are both oscillating with the same period, but the second point is reaching the maximum a short period of time later than the first point. And if I continue to add points, all of these individual points are simple harmonic oscillators. It's just that when they're all moving together, we get a wave. And that's, I guess, my rationale or my reason to explain to you why we even study simple harmonic oscillation in this unit. It's about waves, okay? We then talked at one point in this unit about the horizontal oscillation of a mass on a spring. And this is perhaps one of the more complicated things that we studied. we're talking here about a horizontal mass. We typically draw it as like a box that's oscillating back and forth because it's attached to a spring. And this box is maybe pushed towards the wall and released. It's frictionless, which is really a physics fantasy. It doesn't exist, but it makes it easy for us then to learn about conservation of energy. And the bottom line is that this mass, I'm going to put a little mark on the center of this mass so that we can tell where it is. That's a sticker that I put on the mass. This mark will go from some point over here, which I can call the negative of the amplitude, to some point over here, which I can call the positive of the amplitude, to some point halfway in between. And these are all displacements, and we would say that the displacement halfway in between is x equals 0. Somebody want to remind us, give me 1 second here. The 2 points on the outside, this point and this point, are called amplitudes for position. Does anybody remember what we call x equals 0? Zahar? It is the equilibrium position. So we talk here about that center of that mass being at the amplitude or at the equilibrium position or in between. And when you talk about mechanical energy, and this goes back to Unit 2, mechanical energy is the sum of kinetic and potential. So we learned that the potential energy stored in the mass spring system is 1/2 kx squared. That's mechanical energy. And if mechanical energy is conserved, and you have to listen carefully to this before you write anything, then that means that the mechanical energy at the amplitude is the same as the mechanical energy at the equilibrium position, and it's the same as the mechanical energy in between those 2 points. However, when you start to describe the mechanical energy at, say, the amplitude, or describe the mechanical energy at the equilibrium position, or describe the mechanical energy in between, they have different descriptions. Because at the equilibrium position, what you're talking about is having only kinetic energy. This is at the equilibrium position. Because x is 0, if you were to put 0 into 1/2 kx, and I have a writing mistake up here, who can tell me what I've incorrectly written or what I've missed? The squared on the x. Excellent. So if I were to put at the equilibrium position x equals 0, I put it in here, I get nothing for potential energy. So this is the mechanical energy at x equals 0. Well, what about the mechanical energy at, say, x equals a? Well, at x equals a, that's the point where the mass reaches the furthest distance or displacement away from the center, and that's always the position where the mass changes direction, which means it's not moving there. So at the amplitude, the mechanical energy is solely potential. And that equation that I built there, 1/2 mv squared equals 1/2 ka squared, is comparable to having a pendulum and saying mgh at the top equals 1/2 mv squared at the bottom. So it's comparing the place where you have all potential to the place where you have all kinetic. The bottom of the pendulum is like the equilibrium position of this. But when you're talking about a position that is giving a displacement that's someplace between 0 and the amplitude, or between the negative amplitude and 0, doesn't matter, then at that point in time, what you have is a sum of kinetic and potential energy. And the analyses that go along with these calculations, and you can go back and look at some of them, they were quite complicated, involve using this conservation of energy statement along with maybe Hooke's law at some point, along with maybe Newton's second law of motion at some point. So, for example, if you end up using in a problem this to find out what the amplitude is, what the maximum displacement is, then you can put that maximum displacement in here to find the force on the mass, and then you can put that force on the mass in there to determine the acceleration of the mass. And one final comment here, I hope it's not lost on you that what I've put a green cloud around is an equation you could use. But remember, x here is the amplitude. What I am putting a black cloud around, and this gets pretty messy if you're going to write this down, is also an equation you could use. And I could also set 1/2 mv squared on the left equal to 1/2 mv squared plus 1/2 kx squared. But I want to be very clear about something here. I'm going to change my mind about drawing those clouds. I don't think that's the best visual representation. If I were to solve a physics problem, by using, say, 1/2 kx squared equals 1/2 mv squared plus 1/2 kx squared, I'll just ask you, if I do that, are the two x's in this equation the same x's? No, they're not. How are they different?
One is at the amplitude.
So which one of these, the first x is from left to right, or the second is the amplitude?
Left.
This one is the amplitude. It's the maximum displacement, because that's where there's no kinetic energy. And then this is just somewhere. It's a good way to put it. I was going to say somewhere else. It's just somewhere that's not at the amplitude and not at zero. So you can set any two of those three equal to each other. And that's what we talk about when we say simple harmonic motion or oscillation of a horizontal mass on a spring. Period of a mass on a spring, I'm not going to spend a whole bunch of time talking about this. This was a formula. We did multiple demos with this, and you did a lab with this. I think the lab you did was actually just a kind of a lab exam where I gave you a spring and you had to find the spring constant using the period. So suffice it to say that for tomorrow's exam, you have to know how to use this formula to calculate periods. I will add one more thing, well, a couple things. Or I can give you the period and ask you to find the spring constant. Or I could give you the mass of a planet or moon that the pendulum is on. Because way back in unit, I want to say 2, way back in unit 2, we learned how to find no, I'm thinking of something else. Never mind. I'm going to edit that out. I'm thinking of pendulums. Okay. So you have to be able to work with that formula. Period of a pendulum, similar kind of formula. Period equals 2 pi root L over G. You have to be able to determine values of G from the period. You have to be able to determine the period from G and L. I would go so far as to say that if I give you the period and the gravitational field strength, you should be able to find the length of the pendulum. Similarly, back here, you should be able to solve for the mass in this one. When it comes to pendula, you may also be expected to combine that formula for the period of a pendulum with the formula for gravitational field strength. So if I tell you that we have a pendulum on the moon, and I give you the radius of the moon and the mass of the moon, and I tell you we have a 2-meter long pendulum, you should be able to determine the period. One final comment about periods of pendula and masses on springs. You should be able as well to calculate frequency from this, because you know that it's a simple harmonic oscillator and frequency is the reciprocal of period. And you should be able to do the same thing here. So it's kind of a smorgasbord of different formulas that are all kind of coming together here. Okay, I don't really know what I want to write here, but there was a lesson where it was called Mechanical Waves, I believe. And we went through a lot of material. And what I'm going to say is you need to go and look at that lesson. I'll give you the lesson number so you can find it a little easier. And then I want to discuss everything that you need to know. There's 20.4.5. It was called Properties of Waves and Types of Waves. So there's an awful lot of information in here, and it boils down mainly to definitions and terminology. So for example, you should know that waves can be classified as being mechanical or electromagnetic. Mechanical waves are waves that have a substance that's physical. Electromagnetic waves are things like light, and this is all in this lesson, things like light that don't have a physical medium. In a very broad sense, before I get to the other way we can classify waves, in a very broad sense, you need to understand that energy itself can be transmitted by particles or by waves. So if Nate is standing on one side of the room holding a spring, and I'm standing on the other, I can transfer energy to Nate by shaking the spring back and forth, and the energy moves through the wave and it hits him. But that's a wave transmission of energy. If I wanted to transfer energy to Nate using particles, I would take the spring away from him, I'd tie it up in a big ball, and I'd throw it at him. And then when the spring hits him, it's going to transfer energy, and that's using particles. Mechanical waves, though, can be classified as being transverse in nature or longitudinal in nature. And this is an example of a transverse wave. A transverse wave is a wave in which the medium, I'm going to slow this frequency to a lower level, the medium oscillates perpendicular to the direction of the energy motion. Now, do you agree that when you look at this view with this frequency, it's easy to see that the medium is moving up and down? But it's not that easy to see that the energy is moving left to right. It's easier to see that the energy is moving left to right when you look at this, isn't it? But it's harder to keep track of that point because it's oscillating at a quicker rate. But the bottom line is that dot is moving up and down, and the energy is moving left to right. When you want to track the energy, I suggest that you look at the peak of the wave. And don't worry about the red dot. You just look at the peak of the wave, and you can see that it's moving, if you follow my finger, left to right. So that's transverse, perpendicular. How can you remember that? Well, write the capital letter T. It's got two lines, and they're perpendicular to each other. In fact, everybody, the symbol that we very often use in physics for perpendicular is that. So the two aspects of the wave are perpendicular to each other for a transverse wave. And again, I'm not writing this all down. You can take a look in your notes. When I take a look at a longitudinal wave, and I had lots of other apps that I showed you here. I don't think we saw this one. This is actually pretty good. Take a look at this group of three dots that are crowded together. it's not the same group all the time, is it? You know, it starts off over here, brown, black, pink, blue, teal, blue, teal, green, purple, etc. But I'm just looking, I guess I don't have a way to increase the speed, which is too bad. But when you take a look at that grouping of dots, which is called a compression in this type of wave, it's moving left to right, but each dot itself is moving back and forth left to right. And this is what we call a longitudinal wave. Try this one. There's another one. Close this. So what we've got is a longitudinal wave moving from the bottom to the top. You can see that grouping of lines, which represents a compression, is moving towards the top. But when you focus on any individual part of the wave, every part of the wave is just moving up and down. So longitudinal is where those two aspects of the wave are parallel to each other. I admit I'm stretching for an analogy here that's comparable to the T, stretching your imagination, but if you write the letter L for longitudinal, it basically has two lines which are parallel to each other. Okay, one way or another, you need to know that. You also need to know the terminology for transverse waves, things like crest and trough, and understand that the distance from one crest to another crest is the wavelength, or the distance from one trough to another trough is the wavelength. And you need to understand for a longitudinal wave what a compression is and what a rarefaction is. And don't confuse the word rarefaction with refraction, which is different. You need to know that the wavelength of a longitudinal wave is the distance from a compression to the next compression, or from a rarefaction to the next rarefaction. Tied in with this, and I believe it was in this lesson, was a very important equation called the universal wave equation, which we've used numerous times. And whether it's an electromagnetic wave like light or X-rays, or a transverse mechanical wave like a water wave, or a longitudinal mechanical wave like a sound wave, and you're expected to know sound is longitudinal, water is basically transverse. All of those waves fit into this equation. And we've since talked about the fact that the speed of the wave depends on what it's traveling through, the frequency of the wave depends on the source, and the wavelength is determined by those two things. Speed of sound. You do not need to understand why, because it is quite complicated actually. It's not a simple explanation. But this is the formula that we can use to calculate how fast sound is traveling in air based on the temperature. So this is the temperature in degrees Celsius, and this is the speed of the sound. .331, I guess, would be the speed of sound at 0 degrees Celsius. I would just say to you that you should be able to solve problems that combine this with potentially this, with also this. Right? I mean, if I tell you that I have a tuning fork with a frequency of 256 hertz, and I tell you the temperature of the air, you should be able to find the wavelength. Because if you have the temperature, you can find the speed. Knowing the speed and the frequency, you can find the wavelength. If I tell you the temperature of the air and I say how long does it take between when I speak and when I hear an echo, when I shout against a wall that's 100 meters away, you should be able to apply your knowledge of physics to answer that question. You would find the speed using your formula on the board, and then you would use speed equals distance over time, using that distance and then doubling the time that you get, or doubling that distance to get a time. Resonance and beats. Again, I'm not going to write a lot here, but you should understand what resonance is. Resonance is when you have two objects which have the same natural oscillation. The classic physics example is those two wooden boxes that I have with the two tuning forks. The tuning forks are identical. By the way, the boxes are there just to amplify the sound. Okay? But when I strike one tuning fork and it oscillates at maybe 140 hertz, it causes the air surrounding it to oscillate at 140 hertz. Air does not have a single resonant frequency. Air can oscillate at a lot of frequencies. The air surrounding that tuning fork oscillates at 140, which causes the air further out to oscillate at 140. And that chain of events, like a domino effect, continues until that air hits the other tuning fork, which causes it to oscillate at 140, because it can. But if I have a tuning fork that's 140 hertz and another tuning fork that's 180 hertz, that 140 hertz cannot cause the second tuning fork to oscillate at 180 hertz, because the air molecules hitting it are not oscillating at 180. And the air molecules that are hitting it, which are oscillating at 140, can't cause that 180 tuning fork to oscillate at 140, because it just can't do it. It's like trying to get a pendulum to oscillate back and forth with a certain frequency, and you increase the length of the pendulum. It's not going to happen. It's going to have a different frequency. Beats, you need to understand that when you have two different frequencies, the number of beats you hear is the difference between the two frequencies. Now, not everybody has taken, well, very few of you have taken Math 20. And I'm sure I've talked about this before in this course, but these two vertical lines or vertical brackets mean absolute value. And it just means don't worry about whether you get a negative or a positive. So if I strike 135 hertz, I have that for a sound wave, maybe by stretching a guitar string to a certain tension and hitting it. And then I have another different guitar string, and I hit that one at the same time. I'm going to hear 3 hertz per second, 3 beats per second, which is 3 hertz. You should be able to solve problems dealing with this kind of situation. You know, a classic example is you hear 7 hertz for a beat frequency. That's the beat frequency. And one of the tuning forks is 240 hertz. What's the other tuning fork? Well, there's 2 answers, isn't there? It could be 247, or it could be 233. Is my subtraction right? Yeah. The key is the difference has to be equal to 7. Standing waves and measuring the speed of sound. So I do think it's important that you understand a standing wave occurs when you have something oscillating that's confined at both ends. And what happens is, this is hard to show. This is just a snapshot in time. What happens is it goes from that position to that position to this position to this position. I think you get the idea. This piece of the wave right here, give me 1 second. I've lost an add-on here. I just want to get it back. Oh, that's slow. This part of the wave is simply going to go from that position to the bottom, back up to the top, back down to the bottom, etc. This position is going to do the same thing, but in the opposite direction. So these points where there is 0 energy are called nodes. I'm not going to draw arrows to all of them. They are called nodes, and it's important that you know that. On the other hand, these positions are called antinodes. And in a very general sense, you need to understand that that happens because of interference. What happens is the wave travels from one end to the other and reflects, and it's continually bouncing back and forth. And it's just doing so in such a way that at this point in time where that antinode is existing, which is going to disappear in a minute, it's going to decrease, and it's going to get smaller and smaller. But at that point in time, that just happens to be where the crest of a wave moving to the right and a crest of the reflected wave moving to the left are overlapping. Measuring the speed of sound that's all I'm going to write. I'm going to say a few other things. I expect students to know that when you have a column of air that's closed at one end, I'm talking here about the lab we did with the tube where I would raise the water, that sometimes if the column of air is the right length, you will hear an increased volume of the sound. And the shortest length that will cause that to happen is 1/4 of the wavelength. And the reason why it's 1/4 of the wavelength is that if this is the tube of air, the best way to visualize this, even though sound is not transverse, is to understand that when the waves hit this, they reflect in the opposite direction and they start doing this, producing standing sound waves. I can't draw a standing longitudinal wave. I've tried to wrap my head around what it would look like, and I can't. So we're just imagining that sound is transverse even though it's not. This distance to here, which I am going to clean up my diagram a little bit, this distance to here is the wavelength, which means this point right here where it's loud, there's a lot of constructive interference happening. That point right there is 1/4 of the wavelength. And you will see a question on tomorrow's exam where you have to maybe calculate the speed of sound from that. Or going back to this, maybe find the temperature in the room based on the results. Or maybe if I give you the temperature, find the wavelength or the frequency. This is all tied together. Interference and diffraction. So again, I'm going to refer you to your note package and just speak to this. You need to understand what diffraction is, which is the spreading out of a wave as it passes through an opening. But more importantly, or just as important, you need to understand that the opening has to be smaller than the wavelength in general. And the smaller it is in relation to the wavelength, the more the wave spreads out. So if I had a whistle, and the whistle is inside of a tube and there's an opening there that the sound is going to travel out of, you'll be able to hear it even though you're not standing directly across from the opening. You'll be able to hear it over here and over here. But if I make that opening smaller, what's going to happen is people right in front of it, like Alex, will hear it not as loud. Because that smaller opening is causing the waves to spread out more. More of the wave is doing this, going to the left and the right, than going directly to Alex. But that also means, Ashlyn and Zahara, they would hear it louder. So spreading out means literally taking that wave that's traveling in the original direction and bending it to the left and the right. Interference happens when you have two waves that exist in the same place at the same time. So now what I will tell you, and it's also important for your exam, is these two things you're looking at on the board tell you that the energy is wave-like. Particles do not diffract. If I have an opening, say an opening right here, and I throw a baseball towards the back of the room, It's not going to change direction. It's not going to spread out somehow, smear out through space. And if interference is the things existing in the same place at the same time, if I have a baseball traveling to the left and a baseball traveling to the right and they hit each other, they don't go through each other. Okay? And what you need to understand about interference is there's two types, constructive and destructive. And this is in your notes. This is in the lesson on interference. When you have a crest of a wave meeting a crest of a wave, that's constructive. When you have a trough meeting a trough, that's constructive. If you had a compression meeting a compression, that's constructive. Rarefaction meeting a rarefaction, constructive. And I would say that one other thing here, well, you need to know that when constructive happens, that's called in phase. And when destructive happens, which is crest to trough, that's called out of phase. But I expect you to calculate amplitudes of the interfered wave, of the result of the interference. So if I have one wave with an amplitude of 12 centimeters meeting another wave with an unknown amplitude, and the amplitude of the combined wave, this is a great exam question actually, is 20 centimeters, what can possibly be going on? Can constructive interference be what's happening here? What would the amplitude of the second wave be, Kai? 8. So if we have constructive interference, that means that the amplitude of the second wave, let's call this 1 and 2, would be 8. Because if it's constructive, they're meeting crest to crest and the amplitudes are adding. Is there a different amplitude that the second wave could have? What would the other possible amplitude be? Jay, do you know?
If it was diffracted, then it could be any kind of combination depending on where.
Well, but it has to give us 20.
Yeah.
Okay? 32. So it could be destructive. This is kind of like the beat thing, isn't it? Not quite, but kind of. If it's destructive, this would be 32 because destructive, you subtract the two amplitudes. So I think it's important you understand what's going on here. Constructive means you add the energies together at that point. The energy is represented by the amplitude. Destructive means you subtract. And that leads us, my friends, to the very last topic, which is reflection and refraction. I think reflection is fairly straightforward. The law of reflection simply states that the angle that the wave comes in at, which is called the angle of incidence, is the same as the angle that it leaves at, which is called the angle of reflection. But with refraction, we finished off the lesson on refraction by looking at two situations. And these are the two things you need to know about refraction. And this is in your notes. That if you have a wave traveling from less dense to more dense, what will happen is the wave will change direction like that. But if you have the wave traveling from more dense to less dense, then it does that. You should know that in the less dense medium, the wave travels faster than it does in the more dense, and it has a longer wavelength than it does in the more dense. So the speed and the wavelength both decrease. What happens to the frequency during refraction? Stays the same, because the frequency is determined by the source of the wave. On the other hand, The opposite is true here. That when the wave refracts away from the normal, and those are rays, I'm not actually showing you the ripples or the wave fronts. When it refracts away from the normal, it's going to speed up and the wavelength will increase. So everything about refraction is a qualitative thing that you're expected to know. In preparation for tomorrow's exam, I have, I think, about 20, 25 questions that are practice questions. That's what your exam will contain. 25 questions, multiple choice numerical response. Remember that the split is typically 2/3, 1/3, which means, expect 6 or 7 numerical response, maybe 8, and the rest multiple choice. So what you're working on for the remainder of the class are practicing these problems. I do have a Sabre support tomorrow morning. If you look in Power School, it's probably listed as a Math 30-1, 30-3. You are always welcome to sign up and or show up if you have any questions before the exam tomorrow. Okay? So get to work on those, please. Give me a second to just do a couple things at my computer, and then I'll be around to check on you and help you out.